Good afternoon, everybody. My presentation today is the influence of geometric shape on the performance of the refractive index sensors. And I'm from Federal University of Rio de Janeiro. And this is the outline of my presentation. I will talk about the introduction, objectives, a simulation, and experimental setup, manufacture of fiber in different geometric shapes, performance, and the conclusions. I'll start by talking about the use of optical fiber for making sensors. I present in this slide two types of optical fibers, a plastic optical fiber, I call it POF, and the glass fiber. For plastic optical fiber, it's a much larger diameter, about 1 millimeter, and you do it in a U-shaped fiber, U-shaped sensor. And the glass fiber is something very different. You can do it in this shape. I don't know if this. And let's try to change the pointer as a laser. Okay, so it's a D shape or single mode, multi-mode. Single mode is another kind of sensor, and the FBG, fiber by grating, which is another kind of sensor, very much useful for many parameters. So our previous work in plastic optical fiber, we started with leak detection using a U-shaped fiber for oil, and then sensitivity analysis in different shapes of POF for Escherichia coli, and then for fiber immunosensor for detection of another kind of bacteria, sulfate-producing bacteria. We use also plastic optical fiber for illumination, not for sensor, but solar track for illumination. And another one for hydrogen sulfide H2S for measuring as well, using a fiber just like this, U-shaped. And this is the paper which led to this presentation today. We were invited to present this paper that was published last month. Okay, what are the advantages of using plastic optical fiber for sensor? The first thing is the low cost. It's a very cheap fiber for using. Large diameter, of course, in a large diameter, it's everything is much easier to work with, because it's much easier to put a LED on the fiber and to put a optical sensor, for instance, a photo detector. Easy handling, super multimode, it guides much more light than a conventional glass fiber. Easy to use, and cheap accessories, cutting, polishing, melting, and things like that. But what is the principle of a sensor in format of a U-shape? The light is injected into a U-shape by a LED, for instance, an infrared LED, 806 nanometers. In the curve, the light loses because the angle of intersection between the light and the interface gets too large, and much of the light goes out. And the surrounding refractive index controls the amount of light that goes out of the fiber in the curve, because the critical angle depends on the refractive index of the outside of the fiber, normally water, or other with some other components. So this angle, this is the angle that is critical, depends on the refractive index of the external medium. So the evanescent wave, which is the thing that you are going to use as a parameter for measuring anything that is outside the fiber, is the light turning back when it reflects inside the fiber. And finally, the output light power sensed by the photo detector depends on the refractive index of the outside of the fiber. So we have the power is a function of the refractive index. So anything that changes the refractive index, you can measure by measuring the power on the photodetector. So the depth of the evanescent field is this dp in here. You can calculate it. It depends on many factors. For instance, the refractive index, the angle of incidence, and normally it's about 806 nanometers if you use this the wavelength. So it's just about one wavelength. So anything that will be close to the fiber inside this distance will be sensed by the sensor. So we have to attract things there in order to measure the refractive index. So that our interest at the moment is to detect bacteria. Bacteria, for instance, Escherichia coli, is about 1 micron in length. It changes the refractive index of the water, so that the refractive index of pure water is 1.3. And the refractive index of the pure bacteria, if the bacteria was largely concentrated inside the water, is 139. But it's never like this. The contaminated water does not have so much concentration of bacteria. So the variation of the refractive index inside the water is about 136 to 137. That is on the second position of the decimal. So you have to have a very sensitive sensor in order to detect the presence of a bacteria. So a bacteria could be not alone, could be there other bacteria there. So we have bacteria A, B, C, and D. If you want to detect the bacteria A, for instance, you have to attract the bacteria close to the fiber on this distance here. It has to be on this distance, otherwise you cannot see it. So that how do you do? We have to put the sample very close to the interface between the fiber and the water. So that the idea is to use a antibody close to the fiber. We fix the antibody chemically connected to the fiber surface, and then the antigen of the bacteria will be attracted by the antibody and the fiber, and the bacteria that we want to see will be close to the fiber. In that case, the refractive index will change, and then you can detect it. So this is the whole system. A CPU here illuminates the LED, the light goes down here, and the photodetector, amplifier, and again the CPU, and you have a measurement here that you could use for instance, to the amount of bacteria in the water. So you have to make a calibration formula for connecting amount of bacteria to the voltage of the outside of the fiber, so that you can detect the bacteria you want to detect. So that let's start to the objective of this presentation, which is to choose the best sensor that will be more sensitive for this purpose. We tried 3 different sensors here. This one has just 1 curve. This one has 2 curves, and this one is 3 curves. So which one will be more sensitive? The idea is to improve the sensitivity in order to be capable of see a smaller quantity of bacteria in the water. That's the idea. So we are going to make some tests to check which one will be better. So we made a simulation using FEM to check the amount of light that goes on the other side of the sensor. We input sensor here, we put light in here, and you detect the output and make the simulation to see which output is better for the sensitivity of to increase the sensitivity of the sensor. We have here the 3 sensors, the response of 3 sensors. This is the amount of light that is transmitted by the fiber. Obviously, the sensor S3 is the one that loses more light than the sensor 1 that has only 1 curve. So the idea is the amount of light that is lost increases the sensitivity. That's the question. Because I want to increase the light on the evanescent field. the more the light you have in an evanescent field, the more you will be sensitive to the variation of the refractive index. So that's the idea here. And we made the 3 fibers using three geometric shapes by using a mold made on the 3D 3D printer. And you just put the fiber inside this mold and fix it. Then you put the amount, the mold on the oven for 60 degrees by 2 hours. Then you have the fiber there. So then you have to remove the cladding of the fiber, because the cladding is an interface between the core of the fiber and the outside. By using acetone, you remove the cladding. Then we put the fiber in this simulation here, a light source, illuminate the fiber, a spectrometer to give it the amount of light that is outside the curve. So this is a response for S1 fiber, for using air as a reference and then using water as a reference. Note that every line of this is a different refractive index made by putting sugar on the water, and the variation, this amount of refractive index. This is for sensor S1. This is for sensor S2. Note that by sensor S2, which has just one more curve, the difference between the air and the first water is much higher than the other one. And the third sensor, you have much more compressed here, but the amount of light that is lost is much more. So finally, you have these 3 curves here, which shows the 3 sensitivities. Note that there's 3 sensitivities much higher, because the derivative of the refractive index to the transmission light is much more. So that's the idea of this project. And we compared our results with some other publications. And the one that has the same, more or less the same amount of sensitivity is this microbending tapered epoxy, which is a little bit more complex to make. So the conclusion is that we made this comparative study between 3 different epoxy sensors, and the FEM simulation allowed us to determine qualitatively the amount of light that can be lost in the curve. And the simulated sensor and manufacturer use 3D printed. And the S3 presented the highest sensitivity, followed by S2 and S1. And with small modifications on the shape of the fiber, we could significantly improve the sensitivity of the refractive index with the fiber. So that's the idea of this paper. Shape modification can be implemented by a low cost and easy fabrication. So finally, we do the next step in our research by functionalizing with the antibodies these sensors in order to detect the presence of some kinds of bacteria we need. So that's the reference I used. And I invite you to go to Brazil to see these mountains that we have for hiking sometime next year during the summer.